Welcome back once more. Now we go for a different problem for the support vector machine, what is called soft margin support vector machine problem. By soft margin, we mean that classes can overlap each other. So we don't have like a perfect separation in between the positive and the negative class as before. Actually, in the previous videos, we discussed what is referred to as the hard margin support vector machine. The hard margin means that we have a perfect linear separability in between the positive and negative examples. When we talk about the soft margin, the same doesn't apply. We've got some mixing. Actually, that mixing can be observed in here. Take a look. We're cutting in some place with our hyperplane, but then the positive example in green can be on the other side. We could have like some or few, of course, we hope to be few examples for the positive class on the negative side and few negative examples on the positive side. That's what a soft margin support vector machine means. Of course, this is really close to this is the reality. Of course, the hard margin support vector machine is a nice starting point. But when we go for real world problems, we need to address this soft margin support vector machine. To solve that, all constraints will consider some relaxation over here. Take a look. Some relaxation. This relaxation makes possible that instead of being like greater than equal to 1, each constraint could be like greater than equal not exactly to 1, but to a smaller value. What is interesting about that is that this guy over here, this psi I greater than or equal to 0 will be a new slack variable, or a set actually of slack variables, each one for each example in our sample, in our training sample. Okay, those slack variables will bring some sort of relaxation to our principle. What is the relaxation? For example, here, instead of saying that the constraint should provide a value greater than or equal to 1 for this guy, I could provide some, for example, if I say that psi of this guy is like equals to 2, what's going to happen here is 1 minus 2. 1 minus 2 is minus 1, so it can be just greater than equal to minus 1. That's the same as saying that this hyperplane will bring this point to the other side. Not exactly that, but it's the same as saying, okay, I will accept this point. Besides, it is not on the correct side, I will accept it in my constraint. So the constraint for this point will have a relaxation psi I. The same will apply for this point. This is the hard margin on the left. On the right, we've got the soft margin. All those slack variables then somehow relax a constraint. Somehow say, okay, I don't have to satisfy this constraint as strong as I satisfy, for example, this one, or this, or that, for this point, or for this point maybe. For this one, I can relax. I can just say, okay, doesn't matter. Let's forget about this point. It's almost like that, okay? So instead of having like positives and negatives points like this, I just the closest point as like positive 1 and the closest point as on the negative side as negative 1. I can assume some points are even closer. That's another effect. Instead, besides having positive points on the other side and negative on the other side, I can also have points that are closer to our hyperplane. That's the same as saying, okay, maybe I must have positive 1 for this and these points. This could be like positive 0.5 and 0.5 for this. So what it means is I'm sure about the classification of these guys. What about these guys? I'm not that sure because they are closer to the hyperplane. And for this, I'm kind of relaxing and saying, okay, I will accept some points on the other side of this hyperplane. That's a soft margin problem. Actually, this is just the same as I said before in a different picture. Yeah, I didn't remember. Okay, I need to ensure positive ones for some points at a given limit. Up down here, those would be like -1, -2, -3. And some points are really close to the hyperplane, so I'm not that sure. That's why they are greater than -1 or smaller than +1, because they are closer to the hyperplane. Okay, in this problem, in this original problem, I had the hard margin solution, or problem actually. And I have to rewrite it in adding up my size of I. Take a look. I'm just adding here plus some cost. We call this constant as cost, or cost constant. So the cost of the sum of all size i's in terms of every point I have in my training sample from 1 to m. Why I'm summing up? Because I want to minimize this, and I want also to minimize the contribution of this. Why? Because if I've got an over relaxation, that's not nice, because that's the same as saying that I accept like points, negative points, all points that are negative on the positive side, for example. That's not a nice solution, of course, or the opposite, okay? So in this situation, I'm trying to minimize this, and as well as every relaxation. Remember, this is relaxation. This cost is a parameter defined by the user. That's a big problem. Many people just run support vector machines in packages like, I don't know, like Weka, or in packages, it doesn't matter, like an R package or a Python package. And they just leave the default C parameter. What is the problem with that? Maybe C was set like 1 or 10, but for our problem, C should be like 1000. And you are consider, let's say, a bad value for this C. And maybe you are saying, okay, oh, but support vector machine doesn't work in my problem. It doesn't work maybe because we're not setting up it correctly. We're going to learn how to set this up, okay? We need to satisfy, of course, the constraints. So the constraints are here, subject to this, minus some relaxation, okay? Minus some relaxation, I will accept. I don't have to be greater than or equal to 1 for this times my class, because I accept some exceptions. I accept some points lying on the incorrect side, okay? Every correction or every slack variable, every relaxation has to be greater than or equal to 0 by definition. Okay. Otherwise, if it's something, it's a negative value, of course, this will be like summing some positive, and that's somehow saying that I will consider points are even greater than or equal to 1, like 2, 3, or 4. That doesn't make like any sense. It has to be a subtraction of a positive number over here to make possible to say something like this. Okay, this point is +1, but this point should be +1 because it's even closer to the hyperplane, but somehow I'm going to subtract 2 and make it like acceptable to be greater than or equal to -1, because it's lying on the other side of my hyperplane. Okay, so this is the formulation we have. Just we extend it by adding up this relaxation, and of course ensuring that xi's are greater than or equal to 0. What is the point here? I hope you guys, as homework, solve this problem. considering the Karush-Tucker conditions. And then also try to apply the linear, polynomial, radial, and sigmoidal kernels on top of that. Just pause the video here, try to solve it, and then you see my solution that's coming now. My solution is this. I just took the original problem here. Take a look. Oh, actually, sorry. This is the problem. This is the final solution for the dual problem, considering this primal for my soft support vector machine, my soft margin support vector machine. So this is the primal form. This is the dual form. How did I find it? We're going to see. This is the solution. And this is how we apply it in real-world conditions to classify new points, okay, in our input space. Let's see my solution. So this is the primal form for the soft margin SVM problem. Consider the relaxation that I want somehow to minimize. I don't want the relaxation to be too like great or large. I just want it to be like as small as possible. But of course, I allow it to happen. First of all, Karush-Tucker conditions. I need to satisfy the primal constraints. That's something I will verify later. I need to satisfy stationarity given my Lagrangian. What is my Lagrangian in this scenario? I'm going to consider WB, psi, alphas, and lambdas. You're going to see now, it's basically the same formulation. We have this C times this guy as in here. And then afterwards, I'm going to bring my constraints. Which are my constraints? First constraint is this one, okay? And I have to make it equals to 0, so I bring those terms to this side. This is going to be -1 plus psi I equals 0. So it's going to be this guy, all this guy, times the Karush-Tucker multiplier, alpha I as before. You guys notice the only difference is this guy over here. And there is something else. Remember, as this is a minimization problem, minus sign here, okay? And I also need to ensure that every xi is greater than or equal to 0. How can I make it? I can see this as a constraint. I can see this in the same way I see this as a constraint. So if this is a constraint that is greater than or equal to 0, I can just multiply it by a Karush-Tucker multiplier that I call lambda I from 1 to n for every constraint. Take a look. Negative here because it's a minimization problem. So I need to differentiate my Lagrangian function in terms of W, B, psi, alphas, lambdas, we're going to see. Okay. Next, I need to ensure my complementary slackness. That's something that we need to the Karush-Tucker multipliers times inequality constraints to be equal to 0. Otherwise, the constraints don't binding. I mean, if a constraint, if some Karush-Tucker multiplier is exactly equal to 0, the constraints don't binding. Again, for those guys over here, this constraint of defining the sidewalk in terms of this point, or the support hyperplane in terms of this point, and the support hyperplane in terms of this point over here, are sufficient to make these two guys and those two other points over here unnecessary in terms of their constraints. I explained that before. I think you guys remember. 4, dual feasibility. Dual feasibility, in our case, we've got a bunch of inequality constraints. We've got, just going back, these inequality constraints and those inequality constraints over here. All those must have those Karush-Tucker multipliers and those Karush-Tucker multipliers being greater than or equal to 0, and that is represented in here, okay? For every sample in my training data, in training set. Now I can solve my Lagrangian. How can I solve? I can differentiate and substitute and perform substitution to find my dual problem from my primal that is here. So differentiating in terms of W, I have the same as for the hard margin. Take a look. Differentiating in terms of B, I have the same as for my hard margin problem. When I differentiate in terms of psi I, something different is obtained. Take a look. In terms of psi I, a given psi, one value of psi, I have C minus, of course, this psi I is multiplied by alpha I, so minus alpha I. This very same psi I is multiplied by lambda I, so minus lambda I, as seen here, equals 0 to make our gradient vectors parallel, to make the gradient vector of my objective function parallel to the gradient vector of my constraints for every I from 1 to n. Carry on. Again, what can I do now? I can simplify this. I can actually use this result to make alpha I, bring alpha I to the other side and make it alpha I equals to C minus lambda I. So, you know what is interesting here? If you guys notice, lambdas I have to be greater than or equal to 0 as defined before. As defined because I have to have the fourth Karish-Tucker condition satisfied. So if it's greater than or equal to 0, it could be at the limit, it could be equal to 0. If it's equals to 0, alpha I can be at most equals to C. If lambda I is like 5, it's going to be C minus 5, or C minus 10, or C minus 20, or C minus something. However, alpha I cannot be, take a look, smaller than 0. It has to be at least greater than or equal to 0. So this makes a very nice simplification in our problem. So alphas I must be in interval from 0 to C. So the interval for alpha I is given in range 0 to C, enclosed in both. This means, of course, it can be equals to 0 or equals to C. If you guys define a bad value C for your problem, maybe your alpha I doesn't reach a given value that's necessary to make constraints, to satisfy constraints, and that's why your solution, your support vector machine solution is not good enough. Okay, this is quite interesting. Next, we can perform substitutions. First of all, we are going to substitute W by the sum of alphas times y's times some vector. And we are going to have here at this point this as before, the same as before. We are going to substitute, of course, here there's no W, here there is a W. Wow, so if there is a W here and a sum, I can put the sum outside because it's a linear transformation, and I can get, of course, a double sum of I to n and j to n, as in here. Oh, here should be j, sorry guys, and here it should be j. My bad, guys, sorry. But here is right, okay. So alpha is I, alpha j, yi, yj, and the dot product inside. And the dot product, of course, here inside, as before, as we did for the hard margin problem. If you don't remember, go back. B times, take a look, yi, alpha I, and there is a minus sign. So B is in evidence here, minus B times the sum of alpha I, yi. However, after our differentiation, we found that this becomes 0. You guys remember, it's in here. Take a look. This becomes equals to 0. If it becomes equals to 0, and after substituting, it is vanished from our formulation, I must remember to add this term as a constraint in my dual problem. You guys remember, I'm sure. Again, I will have here -1 times alpha times this -1, so it's going to be plus alphas. I've got also some alpha times psi with a negative sign. Alphas times psi with a negative sign. And of course, here, I can substitute this lambda by c minus alpha. Why? Because lambda can be seen as c minus alpha. Take a look. C minus alpha. That's why we have this lambda substituted by c minus alphas. Oh, that's so nice. From this, we give a next step. Our next step already provides a final solution, as shown here. How can I find that final solution? Take a look here. C times some epsilon, some c, but this c is a negative c. And here we have a positive c. So it's going to cancel out with this term over here. Here we have alpha times psi. Negative is going to be positive. That is going to cancel out with this. So we are going to have this canceled out with a part of this and part of that canceled out with this. So we have a positive half and a negative element. So this is going to be minus half of this plus alpha I. The same solution for the hard margin, but the constraints are different. The constraints, we still have this, which was vanished in our formulation, and alphas I are in a given range, are in a given interval. It goes up to C. If C is not well defined by the user, of course, our optimization for this dual soft margin support vector machine problem is going to fail. That's why some people don't find like the best solution, because they didn't define a fair value for C. If you are not sure about C, define a very large value, because you're going to give room for alpha. The problem is it's going to take a lot of time to optimize if C is huge, but no problem. Better use C as a huge number than define C as something where you are not sure if it's going to work or not. Okay? You know what? Now we have our problem formulated in its dual form. Here is, of course, the way we're going to apply our classification function as before. And B is found actually as before. It is minus half of the closest positive and negative elements summed up, dot product by W plus B. It is in here, exactly what I had. Of course, here we have to find in terms of the relaxation given the closest positive element and the closest negative element I have in my space. In this scenario, I will have this formulation for the closest, and here for the closest from the negative side, given a psi, a negative psi, a positive psi. Summing up both equations, I will have this as a result. Okay, and of course I can solve this for B, and I will have B equals to half of this and half of that. So B equals half of this and half of that with negative signs, just because this guy is going to go to the other side and this is negative, as you guys can see. I just decided to sum up both and use my minus as an F- sign over here. Okay, this is my B for the soft margin problem. What is nice about this soft margin problem that I wish you guys to implement is this solves complex problems. This indeed solves very complex problems. Guys, see you in next videos.